All right, let's go ahead and get started with the second video from this chapter, being Chapter 9 from Physics of Everyday Phenomenon, Griffith, 10th edition. In this second video, we're picking up in section 9.3, Archimedes' Principle. Archimedes' Principle is famous for explaining the concept of buoyancy, the concept of once you submerge something, that submerged object will experience an upward force known as the buoyant force, and that can be a way of measuring the density of an object, because you can then calculate the displaced fluid volume and measure the apparent weight, and then you've got yourself a measurement of the actual, the difference between the density of the object and the density of water. And if you know the density of water, then you've got yourself a density measurement. So it's famous for that, among many other things. So when we talk about Archimedes' fluid, density is front and center because it's all about this concept that the fluid that was pushed out of the way to make something float, or just not be as heavy as it normally is, effectively because of the pushback of the buoyant force, has everything to do with density, all right? Different fluids have different densities, so things will float differently in them. We usually float in water, but maybe you're familiar with the difference between floating in salt water versus fresh water. Salt water being denser, having a higher density than fresh water, things float higher in salt water. All right, there's extreme examples of that. Very salty waters like the Salton Sea in California, where things float much higher. You're noticeably more buoyant due to the extra density of that unusual water. So that's certainly a concept. And if you swam in something else, then you would experience a larger buoyant force for those fluids that have a higher density. Okay, more of you would float above the fluid level. All right, and when we talk about buoyancy, we're going to be talking mostly about liquids, but buoyancy applies to gases. That's how a hot air balloon achieves flight. It has a gas trapped inside of the balloon that is lower density than the gas around it, and therefore experiences a net upward force because the gravitational force pointing down, its weight, is smaller than the force vector pointing up, which is the buoyant force. Okay. So that's what we're getting at here. But let's define density. Let's talk actually a little bit tangentially about the pressure exerted on something due to depth, although that is tied in with the definition of the buoyant force, and go from there. All right, so the average density of an object compared to a fluid determines whether the object will sink or float in that liquid. The upward force that pushes objects back towards the surface in liquids is called the buoyant force. It's kind of like the normal force. Right? The normal force pushes back from a solid, right? Because you push down with your weight. The buoyant force is also a reaction force. It forms a force pair with the pushing on it from whatever the source is, usually weight. Okay? So it's very much like the normal force, mechanical contact force, but it's being applied by something very unlike the normal force that is deformable, that moves out of the way, right? That swooshes out of the way. That's the thing about fluids. So that changes the behavior of the force, changes things it can do, things it can't do, and it then gives it a different name, the buoyant force. So Archimedes' principle, historically, is really the foundation of all of this, states that the buoyant force acting on an object fully or partially submerged in a fluid is equal to the weight of the fluid displaced by the object. So that's so interesting because what we're saying is the buoyant force isn't dependent so much on the object, but rather what the object does. As the object displaces fluid, the buoyant force increases. It's all about how much fluid is displaced, okay? So an object that's completely submerged is displacing an amount of fluid equal to the object's volume. But the buoyant force isn't dependent on the object's mass or the object's density. The buoyant force is only dependent on the weight of water that would be there. So you think about it, if you've pushed the fluid out of the way, water usually, then what happens is the buoyant force is an upward pushing force that is exactly equal in magnitude to the downward weight of water that would have been there. Isn't that interesting? And that makes sense, right? You push the water out of the way, therefore the force is the effect that would have been gravity had the water been there. Okay? Not dependent on the mass of the object or the density of the object, but just on the volume of the object in the case of a fully submerged object. Okay? So the source of the buoyant force is the increase in pressure that occurs with depth. All right, so this is going off, not just saying that, okay, it's about the displaced volume, because that's a wonderful place. And you can sort of stop there and just say, oh, that's your rule for buoyancy. It's just displaced volume. And in the case of something that floats, it's displacing less volume of water than its entire volume, because it has a lower net density than the water, okay? But turns out that doesn't really explain why the buoyant force always points up, right? And kind of where it comes from. So there's to take a step to the side or take a step backwards, there's an explanation that really explains the origin of the buoyant force. And that's what we're going to do in the next 2 slides. So the source of the buoyant force is the increase in pressure that occurs with the increase in depth. There's a figure that will show that in the next slide. But first, let's think a little bit about pressure from depth, okay? Because obviously pressure increases with depth. We know that because we talked about, the depth at the bottom of a barometer, the depth at a depth of 32, the pressure at a depth of 32 meters in water, and how that's exactly equal to the pressure at the bottom of the sea of air, okay, of 101,000 pascals in value. Okay, so we know that idea, but we haven't seen a formula that tells us exactly how it changes. What's the rate of change? Well, the rate of change of pressure in the atmosphere is really complicated. I talked about it. We won't cover it in this class because it's exponential. Okay, but it turns out that the rate of change of pressure in water, okay, the thing that generates most of the buoyant forces we care about, like making boats float, right? Well, and people. That force, and rather that the pressure in the water as you go down into it, increases very nicely with that value, that actual depth value measured in meters, okay? So you have a nice linear relationship, okay? So atmospheric pressure is greater near the surface of the Earth than at high altitudes. The pressure near the bottom of a pool is also larger near the surface, all right? Larger than near the surface, near the bottom. I misread that. The pressure near the bottom of the pool is larger than near the surface, obviously, okay? The weight of the fluid above contributes to the pressure, okay? So it's pushing down weight. So water emerging from a hole near the bottom of a can filled with water has a larger horizontal velocity than water emerging from the hole near the top, okay? This is because of the greater pressure exerting a greater force. So if the hole has the same cross-sectional area, then we've got a force that is larger, right, due to the larger pressure alone, because the area didn't affect these 3 different forces. If you have a larger force, then you're going to have a larger acceleration of the individual molecules of water. That causes them to have a larger initial velocity, and there they are shooting out with a larger initial velocity, causing them to take a projectile parabolic path that is less steep than the ones that experience less pressure because they're not as deep, the holes in the can, that is. Okay? That is a cool tie-in with this idea of pressure and good old-fashioned kinematics. Okay? Now, even if we don't care about the individual molecules of the water, we can still can calculate the velocity of the stream the same way. And it turns out that just using conservation of energy, we can find the exact velocity of the streams of water dependent on the depth. Okay? But all that aside, this concept of increasing pressure and clearly a creation of energy, because in this case it's manifesting itself as kinetic energy because we're giving it a chance by poking a hole, right? Well, that just goes to show that there's energy involved, and what it is it's the weight, okay, which is mg, okay, and then the volume ah. So if you think about it, well, pressure is going to be the work over area. Okay, and we know that because we talked about pressure times area is work. Okay, so we talked about how we had the pressure volume was going to be work. Yeah, you're right, and that's what we're seeing here, right? So we see then that pressure times volume gives us units of energy, right? So then if we then take that, if pressure times volume gives us units of energy, then just pressure on its own gives us units of energy over area. Okay? So that's what we're showing here, kind of extension of Boyle's law if you want to have that direct through line of how these things are related. So pressure is work over area. And the work is the work done by gravity on the layers of fluid, which is just going to be, all right, the mass times gravity times the distance, height. Because remember, gravitational work is just force times distance, okay? But look what we've done with m. Here's the cool thing. We replaced m with the volume of the entire can and its density. This is the Greek letter rho, all right? So we have then is we've got rho g a h over a. So the whole reason then that we've done this and that we've expressed weight in such an unusual way, because check this out. We've expressed right? Oh, sorry, I kept saying it was work. You probably wondered what the heck I was talking about. This is W for weight, obviously. So it's the weight over area, because the force is the weight. All right, I was so tied in, I was so distracted by thinking about it in terms of energy, I didn't notice that it would not work as work. It has to be, so it's force over area, okay? It's force over area. And the force is simply mg. But what we've done is we rewrote mg as rho g ah. I know, that's like, we really expanded it out, okay? And we simply did that because the g remained, but the m became v rho a, okay? Well, rather ah rho, because the v became ah, okay? And then the rho came right out of the fact that mass is volume times density. Density is measured in kilograms per cubic meter. So if I want to know how heavy I am, I could take my volume, multiply by my average density, and that will be my weight, okay? Or rather my mass, multiplied by gravity, and it's my weight. Okay, so that right there is just rate. It is just the expression for weight, a force. Density, gravitational acceleration, area, and height, okay? But again, why the heck would we do that, right? Because if we have some area that's going to cancel out, all right, because we just want a general idea of the pressure, which is exactly normalized by area, which is to say divided by area, then the area is eliminated, the whole point of this expression, okay? The whole point of rewriting mg, and look what we got. We have that the pressure due to changes in depth is rho gh. That's called hydrostatic pressure. I have it in my key formulas over here, because it's such a big one, right? It's such a key idea. It tells you what the pressure will be as you change depth in a certain fluid. So hydrostatic, because it's water, hydro, static because it's at rest, and that's hydrostatic pressure. So this is depth pressure. So if I plug in, 10 meters, 10 meters per second squared, here I am rounding gravity, and I put in a density like density for water of 1,000 kilograms per cubic meter. So then I have 1,000 times 10 times 10. Well, 10 times 10 is 100. 100 times 1,000 is 100,000. So that would give me 100,000 pascals, about 1 atmosphere, for water, because that's density of water, 10 meters of it, which is what we'd expect, because 10 meters is about 30 feet. That's about 1 atmosphere increase. So every 10 meters you go down in water, you get another 100,000 pascals of pressure. And that's what this formula gives you, among other things, okay? And one of the other things that it gives us conceptually, not numerically, is that means every submerged object must have a bottom that's lower than its top, which means there's always going to be an increase in pressure, which means that the net force due to that change in pressure must be up, right? It has to be up. Look at this figure here. We see that there's pressure, and yes, it's all over the place, but when we appreciate that it is affected by depth, we see that the pressure isn't as uniform as we assumed it was in, say, Pascal's principle. And I said, this idea of pressure being, perfectly transmitted is great as long as there's no noticeable change in depth. Well, here, there might not be, right? Because I said it only really matters if it's mini meters or something. Well, this doesn't look like mini meters. This looks like a small block in a laboratory hanging on a metal pole, right? Isn't this centimeters? That's true, right? There actually is a tiny change in the pressure. It wouldn't be this noticeable, right? The actual difference in pressure at the top and the bottom would be very, very minuscule, right? But there is a difference. And the reason that matters is because it tells us conceptually that the buoyant force must push up. It's going to be an upward pointing force, okay? Because pressure increases with depth, okay? All right, and it's proportional to both the height of the cross-sectional area and to, it turns out, most importantly, the volume. So this explanation, this background understanding of pressure with depth, which on its own is an important idea, right? As I have it as an equation, but then have that being a explanation, a justification for Archimedes' principle and the buoyant force, just takes us right back to the same idea that the volume of the fluid displaced is directly related to the weight of the fluid displaced. Okay? That what happens then is we have this idea then that the buoyant force is just the upward pointing force of what would be the weight of the displaced fluid. Okay? So what happens if the density of the object is greater than the fluid? What happens if it's less? What happens if it's the same? Well, if it's greater, then you're going to end up with a net force that isn't zero, and the net force is going to point downwards, and the object's going to sink until it hits something else, like the olive hitting the bottom of the glass. Now there's a normal force, and it's back at equilibrium, back at rest. In the case where you have an object that is less dense than the fluid around it, then you have something floating. Not all of it will be submerged. You're going to have an equilibrium where the buoyant force will exactly equal the weight, okay, and then go from there. And then you can have cases of like organisms that have evolved to be neutrally buoyant, so they don't experience a net upward force. If they balance out, I think what they have like different sacs of kind of air that can adjust their buoyancy, because sometimes they want to sink or float. But if they don't, then they can only move laterally and not focus on moving up and down, because they're neutrally buoyant, no acceleration in the vertical direction. Let's do a quick example with something that floats to hopefully illustrate this idea. So we'll call this buoyancy and floating. And then this will be the end of this video after this, and I'm going to go ahead and talk about fluid motion, because there's a lot going on in the next video. So buoyancy, floating example. It's over here. Okay. So we have a floating object. We'll consider some water. We'll put in a block of some sort, and it's naturally floating, so it's not dense enough to sink. And we have the following information. I'm going to tell you that a floating object floats with 15% of its volume above the waterline. Okay, so that's our information that we have. And then the question is, what is the density of this object? And we can solve this with the concept of buoyancy. So what is the density of this object? Density of the object. Pretty neat way to apply the concept of buoyancy. So you might be not immediately thinking about how this will work. So let's go through the steps, and I think it'll become clear. So there's two forces acting on the object, the force of gravity and the buoyant force. Now you might think, oh, we don't know either, and it's weird that we don't even know the volume of the object, right? Like, how can we possibly solve for this? Don't we need more information? Well, one thing that you'd be given in the problem like this is the density of water. We've been talking a lot about it recently, so I figured I'd write it off to the side, but we will need that value, right? This is the density of water. So rho for water is 1,000 kilograms per cubic meter. Okay? Alternatively, I could ask you for it as just a fraction of the density of water, because just knowing the 15% is enough. If you just wanted it as a fraction, you could say, oh, it's 1/2 as dense as water, or 80% as dense as water, or something. Okay? So what we do here is we think about the forces, and since the object is floating, that means that the net force in the vertical direction is 0, because it's definitely at rest. Every floating object is an object at rest. Okay? So we have that F net in the y direction is just going to be the buoyant force minus the gravitational force. Okay? And most importantly, it's equal to 0. There's no acceleration. This is unlike a sinking object. You could have a system where you've got a sinking object. It's going to be accelerating slower than if it wasn't in the water, like dropping a rock in the water. So it won't experience a gravitational acceleration of 9.8 meters per second squared, because that's where we ignore buoyant forces, which we can reasonably do in the air. But in the water, we can't. Obviously, the rock is going to accelerate, but at a slower rate. And we can find that rate ignoring drag, which is, we probably shouldn't, right, because it's significant in water. But if we ignore drag, then we just have a constant acceleration, and we find that by having some F net equal to ma, okay, for a sinking object. But we don't have a sinking object, we have a floating object in this example. All right, so then we simply then have our buoyant force, and then we'll say that's equal to our gravitational force. And this is where things get cool, because we got to think about what do we actually know about those forces? Well, we know the buoyant force by definition is equal to the weight of the water that was displaced. We know in this case that's going to be the density of the water times the volume of displaced water. So remember, rho times volume, density times rho times v, density times volume, right? This expression right here, this is m. Okay, this is exactly mass. Rho times v is always mass. It's a new way that we can think about mass that's relevant to these equations, just kind of expanding it out, right? It makes sense that density times volume is mass, right? Because it's kilograms per cubic meter times cubic meter. There you go. That's how much mass you have. Okay, so that's the mass of the water, then multiplied by g, right? Because it's mg, And then that's going to equal the mass of the object, which we'll write as the density of the object, so OBJ for object, times the volume of the object, also times G. Squeezed it in there. All right, let's go down to the next line. Okay, so let's appreciate this. So we've taken that equilibrium, the fact that the buoyant force equals the gravitational force. We've taken the couple times we've seen now, definition of the buoyant force is just being the weight of the water that's displaced, so mass of displaced water times G, okay? And this would be M disp for displaced water, D-I-S-P, okay? So what's wonderful about this is a bunch of things are going to cancel, which I'll rewrite it so we can see. So density of water times volume of displaced water, displaced water, times G, okay? Gravitational acceleration, make it a weight, not just a mass. And then density of the object that we're interested in times the volume of the object times G. Okay, G cancels. Now I said a bunch of things are going to cancel, right? Where's the other things? Well, it's the volume part, because we were given information about the volume of the displaced water and the volume of the object. We were told that 15% of the object is above the water line. That means that, well, 85% is below the water line. So that means that the volume displaced, this right here, must be 0.85 times the volume of the object. You see it? All right, so that was the key. So we got the density of water multiplied by 0.85, the volume of the object, equals the density of the object times the volume of the object, which cancels the volume of the object, at least. That's why we didn't need it. And then we can simply solve for the density of the object, and we see that it's precisely equal to 85%, or 0.85, times the density of water, and the density of water being approximately 1,000 kilograms per cubic meter. This nicely becomes 850 kilograms per cubic meter, which is pretty typical of a lot of woods, right? So this is a fairly heavy wood, not the lightest wood, density-wise. So like a hardwood with a density of 850 kilograms per cubic meter, floating in water. How do we know that that it has this value? Because 15% of it is above the water. Okay, that's how when we look at a big chunk of ice, like an iceberg floating in the water, and we see that 10% of it is above water. What does that tell us? That tells us that, first of all, 90% of it's below water, right? Which people always think is really interesting. But also, just by looking at that 10 and 90, we see then that the density of ice is 90% the density of liquid water. Okay, pretty cool, right? By the way, that's obviously really unusual. Most solids are denser than their liquid states. Water is a special case. But hopefully this is a good example of buoyancy and a good kind of thorough way to wrap up this concept. Only got a couple slides here, but buoyancy is a big deal. It has lots of applications, ties in so nicely with Newton's laws. So there's definitely lots of computational potential there. But we'll talk about fluids in motion in the next lecture video. We'll make it 3 because it's just a kind of three distinct concepts. All right. Well, I hope this video has been interesting and informative. See you all next time.